Most machine safety conversations start too late. They start when someone asks, which safety PLC should we use? They start when someone asks, is this light curtain SIL 2? They start when someone asks, can we certify this machine with this interlock? But I want you to pause right there, because the real engineering question is not, what safety device should I install? The real question is, what accident can happen if this safety function fails to danger? That one question separates a checklist engineer from a real design engineer, because me safety is not achieved by adding safety devices. Machine safety is achieved by understanding accident causation and designing safety functions that interrupt that causation reliably. And that is why today I want to talk about SIL assignment for machines, not as paperwork, not as compliance language, not as a certificate copying exercise, but as one of the most important engineering disciplines in automation, instrumentation, process control, and machine design. SIL means safety integrity level, but do not treat SIL as a label. Do not treat it as a product feature. Do not treat it as something you copy from a vendor data sheet. CL is not the safety of a device. CL is the required safety integrity of a complete safety function. And that complete function includes the sensor, logic solver, final element, wirings, diagnostics, software, reset philosophy, stopping time, human interaction, validation, proof testing, maintenance, and lifecycle control. So when someone says this device is SIL 2, your next question should be, but what is the safety function? Because a safety PLC does not make a machine safe. A light curtain does not make a machine safe. An emergency stop doesn't make a machine safe. A guard interlock does not make a machine safe. They only become part of safety when they are correctly selected, correctly applied, correctly integrated, correctly validated, and correctly maintained against a clearly defined accident scenario. That is where many designs fail. They do not fail because the hardware was missing. They fail because the risk was never properly understood. They fail because the safety function vaguely defined. They fail because the designer assumed the operator would behave ideally. They fail because maintenance was treated as a rare event. They fail because cleaning, setting, fault finding, blockage removal, restart, and bypass conditions were not seriously analyzed. They fail because someone selected a SIL rating before understanding the accident chain. And that is not engineering. That is hope. A serious SIL assignment starts with the machine as it will actually be used, not the machine as it appears in the brochure. Not the machine as it behaves during factory acceptance testing. Not the machine as imagined by the design office. The real machine. The machine running under production pressure. The machine being cleaned at the end of shift. The machine being reset after a nuisance trip. The machine being adjusted by a setter. The machine being repaired by a maintenance technician. The machine being restarted after power loss. The machine being operated by a tired worker at 2 a.m., the machine being modified 6 months after commissioning. That is the machine you design safety for. And this is why person type matters. A production operator does not face the same risk as a maintenance technician. A cleaner does not face the same risk as a supervisor. A setter does not face the same risk as a trainee. A contractor does not face the same risk as the original machine builder. A passerby may not operate the machine, but may still be exposed to ejected parts, moving loads, robot motion, or stored energy release. So when you assess SIL, do not ask, is the operator safe? Ask, which person type is exposed, during which task, in which operating mode, and under which failure condition. That question opens the real safety picture, because the person most at risk is often not the normal operator. It is the person clearing the jam. It is the person reaching into the guarded area during setup. It is the person cleaning around residual motion. It is the person troubleshooting with covers open. It is the person assuming the machine cannot restart. It is the person trusting a safety function that has silently failed. That is why a low integrity safety function can be worse than no safety function. Because once people believe they are protected, their behavior changes. They move closer. They enter more confidently. They rely on automatic stopping. They assume the machine will not move. They believe the guard switch, light curtain, safety scanner, or safe speed function will protect them. If that function fails dangerously, the risk can be higher than if the protective measure had never been there. That is the psychology of safety trust. and engineering must earn that trust. Now let us get sharper. SIL assignment is not about worst-case imagination alone. Yes, severity matters. Yes, fatality matters. Yes, permanent disability matters. But severity alone is not risk. Risk is severity combined with frequency, exposure, probability of hazardous event, probability of avoidance, failure behavior, and effectiveness of other safeguards. If every hazard is automatically treated as fatal, your risk assessment becomes blunt. If severe outcomes are ignored because they seem unlikely, your risk assessment becomes dangerous. The better approach is to understand the range of possible harm outcomes. One accident may result in no injury most of the time, minor injury sometimes, major injury occasionally, and fatality rarely. That does not mean you ignore fatality. It means you place fatality in the real accident distribution. That is mature engineering. Because over-conservative designs can become complex, expensive, hard to maintain, and prone to bypassing. Under-conservative designs can kill people. The goal is not pessimism. The goal is truth. And truth comes from accident modeling. Now, one of the most important distinctions in SIL assignment is this. Some accidents are failure-triggered. Others are not failure-synchronized. Let me make this simple. A failure-triggered accident happens when the safety function fails, and that failure itself creates the hazardous event. For example, a control function fails and a machine unexpectedly moves while a person is already inside the hazard zone. The failure causes the accident timing, but a not failure-synchronized accident is different. In that case, the safety function fails first, silently. Nothing obvious happens. Then later, a person opens a guard, enters a cell, reaches into a machine, or performs a task expecting protection. The safety function is demanded, but it has already failed. That is often more dangerous because the failure is hidden until the moment you need protection. This is why proof testing and failure revelation matter. A safety function that is never tested is not a safety function. It is a belief system. If dangerous failure can remain hidden for weeks or months, the probability of it being present during demand increases. So do not write test intervals casually. Do not assume operators will test because the manual says so. Do not credit a test that is not practical, recorded, auditable, and linked to corrective action. And do not confuse indication testing with functional testing. Checking that a light turns on is not the same as proving the machine reaches a safe state. Seeing a guard input change on an HMI is not the same as validating that hazardous motion stops within the required time. Pressing an emergency stop once is not the same as validating the full safety chain under realistic conditions. A real test challenges the function from initiating device to final machine state. Sensor, logic, output, actuator, machine response, stopping time, reset, restart prevention, fault reaction. That is proof. Everything else is partial confidence. Now let us talk about the accident chain. A serious machine accident rarely needs just one thing to go wrong. Usually, several preconditions align. The guard is open, the machine is in setup mode, a jam exists, a person reaches in, a drive remains enabled, stored energy is present, the reset station has poor visibility, the interlock has failed, production pressure is high, the operator is used to clearing jams quickly. The safety function failure was not revealed. That is not one probability. That is a chain. And if you compress that chain into a vague word like unlikely, you lose the engineering. A good SIL assignment decomposes the accident into preconditions. What must be true for the accident to occur? What machine state is required? What human action is required? What environmental condition is required? What fault must exist? What bypass must be active? What energy must remain present? What common cause failure could defeat redundancy? This is where weak risk assessments collapse. They ask, what is the likelihood? A strong engineer asks, likelihood of which event, in which chain, over which time, for which person, during which activity. That is precision. Now let us discuss common cause failure. This is one of the silent killers of safety design. Redundancy is not safety if redundant channels fail for the same reason. Two sensors are not independent if they are both blinded by the same contamination. Two contactors are not independent if the same overload condition welds both. Two software channels are not independent if they share the same flawed requirement. Two cables are not independent if they run in the same damaged route. Two logic paths are not independent if one incorrect parameter download affects both. Common cause failure destroys beautiful block diagrams, and this is why SIL cannot be assigned by counting channels alone. You need to ask, are the channels truly independent? Are they diverse where needed? Are they protected from the same environmental stress? Are diagnostics meaningful? Are maintenance errors considered? Is software change controlled? Is wiring physically protected? Has systematic failure been considered? A redundant safety system without common cause analysis can be a very expensive illusion. Now, emergency stops deserve special attention. Emergency stops are everywhere, and they are often misunderstood. An emergency stop is not a primary safeguard. It is not a substitute for guarding. It is not a substitute for safe access design. It is not a substitute for interlocking, presence sensing, safe speed, safe torque off, or trapped key control where those are required. An emergency stop depends on recognition, reaction, reach, and timing. The person must see the danger, understand it, reach the device, press it, and the machine must stop before harm occurs. That is a lot of dependence on human response. So if your machine safety argument depends heavily on emergency stop use, you need to challenge the design. And if operators are using the emergency stop as a routine production stop, that is not just a behavior issue. That is a design signal. It means the machine may need better operational stop controls, better HMI design, better sequencing, better hold-to-run logic, better access modes, or better fault recovery. Do not hide routine control needs inside emergency stop design. That is how safety functions get misused. Mode selection is another major failure point. Automatic mode, manual mode, setup mode, teach mode, cleaning mode, maintenance mode, reduce speed mode, jog mode, bypass mode. Each mode changes the risk. A machine that is safe in automatic mode may be unsafe in setup mode. A safe speed function that looks good on paper may be dangerous if speed is not actually validated. A bypass may be acceptable during controlled maintenance, but unacceptable if it remains active during production. A mode selector may itself become safety related if it changes which safeguards are active. So treat modes with discipline. Who can select the mode? How is the mode indicated? Can the mode be changed unintentionally? Does the selected mode enforce the required safety limits? Does leaving the mode restore normal safeguarding? Can the machine restart unexpectedly after mode change? Does reduced speed also control force, direction, and stopping distance? These questions are not details, they are safety. Restart prevention is another area where designs fail. Stopping the machine is not enough. You must prevent unexpected restart. After a guard opens, after an emergency stop, after power loss, after a trip, after maintenance, after jam clearance, after reset, after communication failure. The machine must not return to hazardous motion simply because a guard was closed or power came back. Reset should reset the safety function. It should not automatically restart dangerous motion. Production start should be a separate, deliberate command, and reset should be from a location where the person can confirm the danger zone is clear. Blind reset is dangerous. Remote restart is dangerous. Automatic restart after power recovery is dangerous. Restart after fault clearance without awareness is dangerous. Many severe accidents happen not when the machine first fails, but when it unexpectedly comes back to life. Now let us talk about software. Software is powerful. Software is flexible. Software is also invisible. A mechanical guard can often be seen. A wrong safety parameter cannot. A welded contactor can be inspected. A flawed reset sequence may hide in logic. A bad requirement can survive every download. A bypass bit can remain active. A timer value can be wrong. A muting function can be poorly designed. A zone can be incorrectly mapped. A safe speed limit can be misconfigured. A safety PLC only executes what you tell it. It does not make wrong logic right. That is why software and safety systems must be treated with life cycle discipline. Requirements, design, review, verification, validation, version control, access control, change management, fault testing, documentation, revalidation after modification. If you change the program, you may have changed the safety basis. If you change the speed, tooling, material, layout, guard position, drive, sensor, actuator, or operating procedure, you may have changed the SIL assumption. That is why documentation is not paperwork. Documentation is memory. It tells future engineers why the function exists, what accident it prevents, what assumptions were made, what SIL was assigned, what tests prove it, and what changes would invalidate it. If the SIL basis cannot be reconstructed, the design is not auditable. And if it is not auditable, it is fragile. Now, let us bring this back to the practical design engineer. When you assign SIL, do not start with hardware. Start with the safety function. Define it clearly. What does it detect? What hazardous state does it control? What safe state does it achieve? What response time is required? What operating modes does it apply to? Who does it protect? What is the dangerous failure? How is failure revealed? What reset action is required? What restart prevention is required? What other safeguards reduce the risk? What validation evidence is needed? Then model accident scenarios. Who is exposed? What task are they doing? What machine state exists? What preconditions are required? Is the accident failure triggered or not failure synchronized? What harm outcomes are credible? What test frequency is real? What common cause failures could exist? Then assign the required integrity. That is the correct order. Function first, risk second, integrity third, hardware fourth. Validation always. Now, where can AI help? AI can help tremendously, but it must be used responsibly. AI can help extract hazards from machine descriptions, layouts, operating manuals, maintenance records, and incident logs. It can prompt you to consider person types you may have missed. It can identify use cases, activities, modes, and foreseeable misuse patterns. It can generate accident scenarios for engineering review. It can suggest possible preconditions. It can flag common cause failure candidates. It can compare validation plans against the safety function specification. It can help build self-documenting workflows for SIL assignment. It can help engineers avoid blank page bias. But AI cannot own the safety decision. AI cannot validate a machine. AI cannot inspect the wiring. AI cannot measure stopping time. AI cannot sign off life cycle responsibility. AI is a powerful assistant. But functional safety still belongs to competent engineers. So if you are a trainee engineer listening to this, here is the mindset I want you to carry forward. Do not be impressed by safety labels. Be interested in safety functions. Do not ask, is this component certified? Ask, can this complete function achieve the required risk reduction in the real machine? Do not ask, what do we want? Ask, what SIL does the accident model require? Do not ask, can we pass the audit? Ask, can we defend this design when something fails? Because something will fail. A sensor will fail. A relay will fail. A contactor will weld. A cable will be damaged. A software change will be made. A bypass will be requested. A maintenance technician will improvise. An operator will take a shortcut. A production manager will push output. A machine will behave differently after years of service than it did on commissioning day. Your safety design must be ready for that reality. That is the difference between compliance thinking and engineering thinking. Compliance asks, have we installed the required device? Engineering asks, will the machine remain safe when the foreseeable failure happens? And that is the heart of SIL assignment. It is not a form. It is not a matrix. It is not a shortcut. It is the disciplined translation of accident understanding into safety integrity. When you do it casually, you create hidden failure modes. When you do it rigorously, you create machines that are safer, more maintainable, more auditable, and more defensible. The best safety systems are not the ones with the most impressive certificates. They are the ones whose functions are clearly defined, whose assumptions are visible, whose failures are anticipated, whose fallbacks are deliberate, whose tests are real, and whose integrity matches the risk. That is engineering, and that is the standard we should hold ourselves to. If this helped you think differently about machine safety, SIL assignment, functional safety, instrumentation, automation, and process control design, like this podcast, share it with your engineering network and subscribe to the channel for more deep engineering white papers, tutorials, and practical design insights. You can also follow my LinkedIn newsletter, where I share sharper breakdowns on instrumentation, process control, automation, functional safety, engineering design thinking, and the design mistakes that quietly shape real plant and machine risk. Because the future of engineering does not belong to people who only install systems. It belongs to people who understand why systems fail and design them so failure does not become disaster.